Hello everyone, welcome to the last lab of design compiler. So till now in all the labs of design compiler we were doing top down synthesis. Now let's look at a sample design and let's try and do a bottom up synthesis. Now bottom up synthesis is we will use, I'll also show you the characterize and write script method that is used in this lab. This lab is directly taken from the semester documentation. So it uses it's an old lab. It uses compile command, not compile but that should not bother us. Plus, the characterize and write script method is although not very popular nowadays, but at least with this lab you can understand how to set up a design environment for yourself. This lab has multiple skills that are being used, so it shows a good usage of source.synopsis setup. So although the methodology is slightly old, but it still gives us a good insight into how to build our scripts and what to check, how to make sure that design is netlist are written at a particular place, and how to arrange our directory structure and so on. Let me give you some. Let me discuss some summary about the design itself. This design is the same that we use in lab 2. So it is a small design. So the top level is called chip level. It has an adder block, adder 16. It has a comparator, a mux mod, a multiply 8x8, multiply 16x16 path segment, and there's a cascade mod inside which it contains adder, counter, and a comparator. So what we will do is that usually chips are built like this. Instead of small designs like multiply or comparator here, the chips will have big designs. For example, an LCD TV chip will have blocks like USB, HDMI, CPU, and so on. Now, so the idea here is that so when you want to do chip level synthesis, you cannot, for a big chip, you cannot just feed in all the RTL files and do synthesis. It is not feasible because first of all because of the capacity limitation of the tool. Secondly, even if let's say design compiler was capable of parsing so many files, still synthesizing chip level is not how to say, it's not intelligent. Why? Because nowadays in industry different design teams own different intellectual property. Like some team would own USB, some other team would own HDMI. And if you are synthesizing chip, every time there is a design change in HDMI, you are also synthesizing all the other IPs, right? So that's why bottom-up approach makes much more sense, wherein we synthesize the underlying design first, and then at the chip level we will set these designs as don't touch, and we will compile the chip level. Now, how to do this? So this is clear that in bottom up that the bottom level, the hierarchical designs could be synthesized separately, and then they will be stitched together. The top level, the chip level is usually does not contain any logic, or even if it contains logic, it's very non-time critical and it's very small, so that you actually don't need any optimization techniques in the top level. You just need to RTL is mostly structural in nature, so you just take it through compile flow to make sure that it is stitched correctly. That's the only concern. But now major concern is regarding the blocks themselves. Now let's say I am synthesizing USB, which is part of my chip. I need to have good timing constraints for USB. If I am synthesizing CPU, any block I synthesize that is instantiated in my chip should have good timing constraints because the optimization depends on that. Now consider so now we will so ideally every design team will write its own set of constraints. It will, because it knows what all blocks are there, how they are used in the design. The only concern here is that what about the interface logic that two IPs are talking to each other? What about that interface? Now that interface is the only concern here. How to make sure that that interface is optimized properly. For this you have set input delay, set output delay. Now the method discussed here, which is the characterized write script method, it is aimed at solving that problem. So it is a two-part compile in the sense that it has a lot of scripts. I'll discuss each and every script. So the basic flow is that at first level, first of all, for let's say now in this example, we will synthesize added all these blocks: adder, cascade, comparator, multiplier, 16, mux mod. All these designs are synthesized. So each design that is synthesized separately should have its own set of constraints. First thing. Second thing, in this example, cascade model is synthesized, and here since the comparator at top level and comparator inside cascade mod are both same. In cascade mod synthesis, comparator already existing comparator synthesis is taken and it is set to don't touch. And adder 8 is not synthesized separately, adder 8 and counter. So cascade mod, if you look at cascade mod level, it is synthesized top down, but the chip level is synthesized bottom up. So first pass, we synthesize each of them with some default constraints. We will assign some input delay, some output delay, and we will synthesize them. In the next part is, and then we will ask DC to characterize. Now what DC will do based on the first pass synthesis, timing data, it will allot timing budgets. It will assign some input and output delays to the interface signals. For example, let's say a signal is traveling from ADDR16 to cascade mod. Its input at the level of its output at the level of ADDR16 and input at the level of cascade mod. Based on the timing data this has, it will assign some output delay at ADDR16 level and some input delay at cascade mod. Simply, the part delay, the total part delay, it knows the total part delay of that interface from ADDR16 to cascade mod, and it will now break that path, and whatever timing it sees on the ADDR16 side, it will go as input delay on cascade mod side, and whatever timing is consumed inside cascade mod, it will go as an output delay on ADDR16. So this is the way it will assign input and output delay. So that's why first pass synthesis is necessary. One pass is necessary at least to give DC the timing data. If let's say there is no synthesis done, DC will not have any timing data and it cannot characterize. So before characterize, one pass compile is needed. Now the second pass compile is done now, and then characterize, the output of characterize command is using a set of scripts. So that's why we call it characterize and write script. So we write this into these input output delays and whatever plot information into separate files for each design. Now in second pass we recompile the design, so that this time the compile process is much more accurate than the first pass. Now, but in the industry there is a slight twist to this method that we use. We do not use characterize write script because see to characterize and write script to work, the complete design, although in the second pass all these are in the chip level synthesis, all these are set as don't touch, they are not touched, but still the complete design data is present in design. Now consider this problem at a chip level. At chip level, complete 100% design data is inside DC and it is writing characterize, it is doing characterize. If you try and do it for a big chip, the characterize will take long amount of time, big amount of time, lots of time, and that defeats the purpose. So what we do at chip level is that first thing in the industry, what we do, first thing, let's say now the blocks are USB, CPU, so each design team will carefully write constraints for HDMI, USB, and CPU. There will be separate teams, groups working on these, and let's say one person from each group will actually spend a lot of time in making sure that the constraints are okay. Since these constraints will never ever be characterized by DC, these are owned by the user, these are generated by the user, by the designer. So the designer will work on the constraint. He will assign input and output delays which are slightly more aggressive in nature for this block. Plus, the designer has to make sure that inputs and outputs are registered. If the inputs and outputs are registered, it is very easy to work out the input output. There will never be an issue at this point. So every block has its own constraints. Every block will go through synthesis. And now at chip level, what I will do, I will not even read the complete design. I will read the chip level, but now I will read a file, that a Verilog file which is generated from, let's say, for CPU. There will be a CPU netlist, but from this CPU netlist I will generate one more file using some script or some tool that will only contain the CPU module definition with inputs and outputs and nothing else. So it's a black box CPU. There are many, you can do it through script, through Unix script or Perl script. You can easily write out a black box Verilog module out of a netlist. The only information you need, you can even do it from RTL. The only information you need is the module definition and inputs and outputs. That's it. No logic. Now I read, when I read the top level chip Verilog, I read the CPU. Let's call this a black box model. So I'll read CPU black box model, I'll read USB black box model, I'll read HDMI black box model. And what I'll do is I will set them as don't touch. And I'll compile my chip. It will take few minutes. My chip netlist is ready. And then later in this chip netlist, I will remove the black box again using even design compiler. I will remove this. Now I'll read the complete netlist of USB, HDMI, and CPU, and I'll write out this file. So this way, no command in DC, none of the commands in DC except the rise and log in the last will see the complete design. So you won't have runtime issues. This process can be done in few hours, few minutes to few hours. Plus, you are assured that, and then you will obviously do pre-out SP and then post-out SP at chip level. Now, if you have if you see any interface that is violating and that is not optimized properly, you can now feed this back to designer, to the respective designer, or to ask him to correct their port constraints, their input and output. This is how it works in industry. But this again, respective of the method, see, the method is exactly same. But in characterized write script, the correction of input and output delays is being done by DC. But when it comes to big chips, the characterized will be very time consuming. So what we are doing this process kind of manually, and sometimes manual works better than automatic. Sometimes, for example, in this case. But irrespective of the differences, whatever lab we see now, whatever set of scripts we see now, they will be very helpful for you if you go and work in the industry. Now you begin to understand that how things are done in big chips. So let's look at so this is the directory structure, and so in the RTL has all the files. We have already seen that the chip level contains all the instances for U1, U2, U3, U4. So it has 7 instances. Then let's go to, so again work is where we will work. I have created directories here: netlist, log, db, tdc. These are the output directories. So I'll write out all the netlists in the netlist directory. I'll write out all the logs in the log directory. I'll write out all the dbs in the db directory, or db or ddc, whatever, in respective directories. And then these are the scripts. Now we have a lot of scripts. First and foremost, as I told you, each design will have its own script, starting script. The second set of scripts will be generated by characterized write script. So here, let's see the script for, let's say we pick up a design adder 16. Let's see what adder 16 contains. So we have adder 16 dot tickle. So here we define some variables. These will help us in writing out the report and the log for this particular design. So report file is adder16.rpp, design is adder16. We set the current design. We source the default, some default constraints. I'll show you what default constraints contain. I set some design environment. These are just estimates at the first step. We define the load on S out and C out. We set the driving cell to something, I of something on all the inputs. We set drive 0 to clock name. Now this clock is defined earlier. I'll show you where. And we set some input delay and output delay. And then we do a compile, and then we do a write format. We'll write down the DBC, and then we will source a script which will do the reporting. So what will happen in the start is that I will read the complete design, and then I'll change the current design to each and every hierarchical design, and then I do compile at that level. Regarding loads and driving cell, it's alright, but in some of the designs there will not be any clock, and in some of the designs there will be a clock. So this is where we take care of this default constraint. Here I define the clock period and these procedures: size of collection, get port, CLK. If there is a port CLK, we create a clock. If there is no port, the second procedure is checking if there is no port containing the clock name. If there is no clock, then we create a virtual clock, and the clock name will simply be either CLK or VCL. So any hierarchical design, if there is a clock port in it, then the clock will be created. If there is no clock in it, then a virtual clock will be created, and input and output delays will be assigned with respect to either the real clock or the virtual clock. Then again, the set load is set to default load. There is some default driving cell is set. I change this. It should be out of x2, which is in the library, and then it will set drive 0 on a real clock input delay. So these are default constraints, and I'll also change the operating conditions. I'll correct the operating conditions to be so. So every design we will let's see now how do we. So you have the these are the adder, cascade, etc. These are the constraint files with respect to each design, and then there's a report file which will just report out everything into one single report file. Now this report file, it uses variables called log path and report file. So log path is defined in .office DC setup. I will show you. Report file is something which is specific to each design. So you get one report with respect to each design. There is a read command with a read.tcl in which we read all the files, all the verilog files. Then there is a synopsis DC setup which is in the work, where we set the search path, the link library, target library, and so on. And here we define the source path, the script path, and so on, so that we can use these variables called .log path. So you don't need to. This is a very useful tip, that you define some variables related to paths in .office setup or some common file, so that you can use this variable. And then when another user wants to use your set of scripts, you can use it without modifying a lot of files. He can just modify a single file. He can just set some variables, and then he can proceed. He doesn't need to worry that, let's say you were given 20 scripts, he doesn't need to correct in each and every script. He needs to just correct these things in just one script, what is specific to his case, right? So it's a very good way to set up your work area. So this is how you define your variables, and you keep the common stuff in .office setup. And then there is a top level run command, run.tcl. So I will start. So I will not source this directly. Although once your environment is stable, once you have resolved all the errors, you can keep using this file again and again by directly sourcing it. What I'll do is I'll source single statement at one time. So first statement that's sourcing is initial compile. So let's see what initial compile contains. Initial compile. This statement will read the complete RTL. As we saw, read.tcl contains all the read commands. It will set the current design. It will source the default constraint. Now default constraint is simply it will set the clocks and so on, default loads and so on. It will select the worst case operating condition, and then we read these 7 tcl files. The 7 tcl files are nothing but these are specific tcl files for each design. We saw one for adder 16. Let's see one for path segment, for example. So again, it will set what is the report file in design name. It will set the current design. Now see, since we are compiling the underlying hierarchies, we have to change the current design, and then it will again source the default constraint. So any overrides you can do it here. So for example, input delay, output delay, any load or driving cell overrides should be done here, and then it will define. So now in this place you can do specific stuff which is some special stuff which is specific to each design. Default constraint is something that is default, and these specific compiled files for each design, you can do something specific here. For example, in Cascade mod, in fact, Cascade mod is in hierarchical design. It contains some 4 instances. A Cascade mod in turn contains, for example, Cascade mod contains adder, comparator, and counter, and we have counter which is we have synthesized separately. So here the counter is set to, sorry, the comparator is synthesized separately. So it says that use compile once, don't touch approach for comparator. So this lab is just giving you, is showing you ways how you can do stuff, and one of these ways could be applicable to your design when you're working in a project. So this is how you do a don't touch, and then at the end of each compile step, the DDC and the report will be written out. So let's do the initial compile step. We'll open decision. Okay, let's go to work and open decision. So meanwhile, let's also clean up the report areas because I have been running this earlier. So log, I'll clean up this report. BBC. Okay, now I will source the first statement of the run command, and I do this source in script path. Script path is already set to something. Let me show you what script path is set for. Script path was set in .synopsys DC setup. So opening, when you open decision, you should make sure that whatever is in your synopsys DC setup is in fact loaded already. So let's look at link library set. Let's look at the scripts path. It's set to the parent scripts. So now we will source this command. So it will now start reading all the design files, underlying design hierarchical, and it will start synthesizing. So this synthesis, whatever you see the log messages, this is taking place at hierarchical level. It is going to each and every design. It is sending current design, and it is running the compile command at that particular design. So each design will have a DDC out and a setup and reports. This will complete pretty quickly. So we see that there are flags, there are negative flags in some of the designs. So this design has a lot of negative flags. So it is taking some time. I've given a very aggressive clock frequency just the experiment. So now let's look at the report directory which was set to log. So now these are the reports with respect to each and every design. Let's open them. Let's open them and see. So, but the thing is that now the report constraints. Let's first. So the report script that did the reporting for us, it dumped everything into every kind of report into one single file per design. So there is one single file per design in which there is a check design, report area, report design, report cell, and so on, report constraints, when you solve violators, and so on. You could choose to create separate reports for separate commands. It is a personal preference, and you can choose to do whatever you want. But obviously, it is good to have separate reports for separate design, and plus maybe even a timing report which is separate because that is more important. So let's look at the reports now. So now these are the reports. This is the area report for adder 16 and report design, then report port. Let's go to end and see what are the. This is the what are the timing violations we can. This is the QR report. We see that. Let's go to report constraint. or let's go to violated. Okay. So report constraints minus all violators tells us that max area is, we set the max area to be 0, although it is not needed to set this constraint. DC will work the same otherwise. Slack is obviously minus 459 because the area is 459. Then here it tells us that there are some endpoints that are violating because I have set a very aggressive clock. There are endpoints that are violating. Now it tells us what is the timing. Now see here. Okay, the input group is fine. Input timing is fine. The rest of the timing is also fine. What is violating is, let's go to the violated ones. That's all. Okay. Okay, fine. That's all. Okay, so report timing is telling us, okay, the flag is positive. So the report is constraints is not all violators because yeah. So this is the report constraint and the max path. This is the report timing command, path type end. Path type end means only it will report only the endpoint, so everything is routing here. The only thing that is violating is the area. So we are fine here. Let's go to the next one, which is cascade mode. Now cascade mode has is again a kind of a hierarchical design where you have two adders, one comparator, and you have two adders, one comparator and one counter. So again, let's search for violated. So now there are some timing violations here, and seems like there is a GTech component, which is very strange. That means this is because this GTech component is because let's check the script running script. We need to debug why there is a GTech here, and there are violations. Obviously, it will report the. I think it's set to report only the worst part. There is a violation from input port and so on. So we need to check why there is a don't touch here, why there is a GTech here, and then we look at COM16. There is a report clock. Yeah, so there is a virtual clock here. We see that it does not contain any clock code, so we have a virtual clock created. It has violations because okay, one thing that output external delay is said to be very high because the clock period is high. This is because I have set the clock period again very aggressive, but the delays were with respect to slower clock. So you see some violations here. That's okay, good to have because now DC will adjust these. Now DC will adjust these input and output delays and make them more realistic, right? So okay, let's so there are similarly there are reports for each and every design. Right? Now let's debug why did the cascade mod had GTech components. So the problem is that the cascade mod it has a GTech is because we have set don't touch on U12. Now let's open U12. So it's a good test case for us. We get to debug some problems also. Let's open the RTL and see cascade mod, and we see that U12 comparator is set as don't touch. Now, when we compile for the first time, and if the underlying design, let's say U12 here is set to be don't touch, but U12 is still not compiled, comparator is still not compiled. The script here, it is reading the RTL, the initial compile thing is reading the RTL. It is reading the RTL here, and now it is sourcing. So when it comes to cascade mod, it is set at don't touch. U12 is set at don't touch. So DC in fact never gets to compile the underlying the design that is U12, which is comparative. So second pass it will get corrected. Probably, and let me see. If not, then don't touch here is not correct. So in that case, we need to remove the don't touch, and we could read the either we should compile the comparator again, the first thing, and then when we come to cascade mod, we should read the comparator network. So there's a problem in this set of scripts is that it is setting don't touch without even compiling the design. Now let's see if this problem gets corrected in subsequent steps. So this is where initial compile is where we do our first compile. What is important here, which is very important thing, is that you should have proper timing constraints for each of the underlying blocks. Although if you are using characterize and write script, you can start with some basic assumptions, right, with respect to input output links. Now let's again set the current design to be chip level. Let's go back to DC session. Also, let me show you that ADCs are written here. Is netlist written? I don't think so. Netlist is not written. Okay. So let's set the current design. Current design. Always remember, if you are doing design change, current design, if you're using current design a lot and you're changing to hierarchical design. But before doing any chip level, any top level stuff, please remember to change the current design to top level, whatever is your top level. And now it is writing a DDC, which is okay. We'll write out the chip level DDC. So it's always good practice to write out DDCs in between, so that your snapshot is taken. And let's say if you want to debug what happens before the characterize command, you can load up this DDC and see. So now let's do the subsequent step, which is characterize. Now we need to characterize. Now let's see what characterize command, what characterize script is doing. There is a script called characterize. Now this characterize script changes the current design. So this is yeah. So this will, what it will do is that it will characterize. It will go to chip level. It will characterize U1, then U2, then U3, then U4, then U5, then U7, U6, U7. It will characterize. When you characterize, DC will calculate something, and then you can write script. The format is DCTCL, and you will write out these scripts. Now these are now the updated timing constraints. I'll show you what each of these constraints contains, and then it is doing. So what it's doing in the last, it is now what you could do is that to each of these timing constraints, if you want to add any specific command for yourself, by you are doing, let's say you want to do some specific stuff like here, it is grouping the design melt into, and it is grouping this design, is creating a new group, and it is adding this command, this group cell, this group command to the path segment. We will see what effect does it have, and then it is format is DCTCL. Yeah, so it is characterizing U7, then it is changing the current design. So current design changing is necessary because if you don't change the current design, DC will write the path information in terms of the top level hierarchy. You want to make sure that hierarchy is correct for each and every design. That is, the script should be at the top. The script should be written after the design is set to that particular current design. In the sense that, for example, that you want to characterize and write script, you will characterize from top level, but when you do want to write script, you will have to change the design. For example, for mux mod, you want the mux mod timing constraints to be specific to mux mod and not contain hierarchical references to chip level. That is why you characterize from top level, but you change your current design, and then write the script. So here, current design is changed, is first characterized, and then some particular command, whatever special thing you want to do, is written into the script. This command is written, and then this is written into, this is redirected, and this is appended, and this write script is also appended to it. Let's see what we will learn characterize now, and see what happens. We go back to DC, and we will. So see, every source command has a $script path, which is a variable, and the script path is set to. Now this can be set in dots, and also be set up to anything wherever your scripts are. So if you are changing the place where you keep your scripts, you don't need to change these all the other scripts, right? This is why the variable when we define variables that control the path, it is better to define all of them at one place in one single file. So now it is doing something, and it gave an error. We will correct this, and we will characterize again. Okay, let's correct this. DCTCL format is not valid. Okay, so DCTCL format is not okay. So we have to. Okay, this is the problem. There's no space. Okay, so we will source it again. It's not a problem. We can do characterize again. It doesn't matter. So now at the end of characterize, I mean each write script we are writing a DCTCL file into the scripts directory. Let's now see what DCTCL file. Let's see it for. Let's open all DCTCL files and see what it did. So now see it is setting the current design to the adder 16 units, operating condition, Y load model, particular Y load model, whatever is selected. So whatever DC did as part of its synthesis, plus it evaluated the timing constraint, it will write everything in the DCTCL. The driving cell, the Y load model, whatever should be used based on the Y load model selection criteria, area based, and fan out number, then load, whatever it found. See now these loads are not some dummy numbers. These loads, since we are using characterize command and already one pass synthesis is done, DC node what load to expect here, the real load, the real fan out load, not the dummy or estimated load. So that's why you see numbers, such accurate numbers. So this is where characterize helps you, right? This is where there is a system in place which will, from a one basic synthesis stuff which is already done, DC lets you calculate the accurate environment conditions and more accurate than the earlier pass. With each new pass, if you notice, this is simply not a 2-pass procedure. Although minimum 2 pass is needed, but you can also have a third pass that will still improve accuracy. So many people they will do a 1 pass basic plus 2 pass characterize. Many people will do just 1 pass characterize. It just depends on the quality of results that you are getting out of every pass. And now the input delays. Some of the input delays are now here the input delay is 1.2. Now this probably is coming from the chip top level. There is a fixed input delay for every port. That means this input delay is coming from this particular port of adder 16 is coming from the chip top, and there is little or no connectivity. There's a simple net. There is no gate. That is why all the input delays are 1.2 and they are same for all the input ports. But output delay now changes for few ports. Output delay becomes much more accurate for S out because this port is going to some other design, some other hierarchical design. We will see it in the RTL. So it is defining max and min. Let's see. Let's go back and look at the RTL. Let's look at the RTL of chip level. So chip level, let's look at adder 16. Data 16A is coming from chip top. That's why whatever input delay we gave at data 16A at chip level is transferred to AN because there is no cell in between. But S out is going to other hierarchical design. It's going to comparator. It is going to mux mod. So DC based on the interaction of adder 16 with these two has now worked out an output delay. So we saw that S out has some output delay. Then A in and B in have fixed input delays, and this value of 1.2 is coming from the default dot constraints. In default dot constraints, we applied input delay 1.2 on all inputs. This is where it is coming from. So now I think you would have started appreciating how characterize command works. You have to do 1 pass synthesis from this netlist, from this timing information. DC will now calculate. It will calculate output load, it will calculate input delay, it will calculate output delay, and so on. Right? Now let's see what is the next step. The next step is the second pass compile. So now it is saying remove design minus all. Now we have to clear. Remove design. We will do remove design minus all. It will remove all the designs, and then we are doing something with the recompile. We are sourcing a recompile script. Now let's see what recompile is. What recompile script is doing. Recompile, obviously there it's reading RTL. Now we start from the RTL. So see now the first pass you had your own estimated input output delay and environment conditions for each design. After characterize you get more accurate numbers, and now you want to start from RTL, not from the netlist. It's always better to start from RTL. So first line we are sourcing we are reading all the RTL files. Sourcing of default constraints, and now we source the DCTCL. Compare. This is the recompile, and this was the initial compile. This is the initial compile. Initial compile was also reading. It was doing the same thing in the top, default constraint. It is doing the same thing in the top. But these ones, these specific design specific constraint files, are now replaced by the DCTCL file. Now DCTCL file by default is inside the current design. We saw that. So now this is reading DCTCL. This is now the synthesis script. It replaced your own estimation, right? So this is why, see, the other thing to appreciate here is how these script files are arranged. Yes, arranged so neatly that it is very easy now to replace anything or replace any design. Even if your design changes a bit, it is very easy to do modifications. So spend some time in also understanding how these scripts are arranged. This way you will learn when you will work in your project or in your industry how to arrange your constraint files. Now after sourcing this, compile command is run, and then again we will write out the DB, and again we will write out the report, right? And okay, we will not use this. We'll also look at the cascade mod. Okay, now let's now see path segment first. That's something special because path segment DCTCL. So TCL is the one that user wrote. DCTCL is the one that design compiler wrote. So current design. So this is where something special was added. A group command was added, and a new design mult is created, and mult and U100 cells are combined together. Let's see in the RTL whether we can correspond. Path segment.v. So mult and U100 and yeah, U100 is combined together with. Okay, I'm not sure why group command is used here. Minus cell mult and U100. Okay, I'm not sure why a group command is used. I think it's just to show you that whatever stuff you want to add, you can change the current design and you can add it in the same DCTCL itself. So let's now source this. One more thing. We need to look at the cascade mod. Again, we look at cascade mod.dctcl and look at what happened to U12. So again, set don't touch is set here on U12. Let's see if it really solves the problem. So we see that clock definition is also there, everything is there, and let's say for a block that does not have a clock, I guess mux mod doesn't have a clock. You have clock. Add 16. It also has a clock. Comparator, I think this doesn't have a. So okay, it also has a. Okay, this is now a virtual clock because there is no. Okay, there is a port clock. No, it is not created on. This create clock is not created on any port, so that's okay. So so this in this case the clock is a virtual clock. So virtually every information that is needed for synthesis is written out by characterized writes. So we will now source this, recompile, So now it's doing synthesis, and now let's see whether it contains as many violations as earlier. Now we see that earlier we were seeing a lot of violations because we gave. So what are now there are few violations. Why? Because the input output delays are becoming more and more accurate. Earlier what happened is that the original script had the clock period of 12. I changed the clock period to 5. I made the clock very aggressive, but I did not play with the input output delays. So input output delays for this example in earlier case were actually very bad values, and that is they were bad values. And then the characterized write script now showed us that DC now calculated accurate values, and now at least the hierarchical design synthesis is going on faster, and now you don't see violations. Now let's look at the reports now. So now earlier the reports were .rpt, now the new ones are DCTCL.rpt. So let's look at the violation in one of the designs. Let's look at there were violations in, let's say, multiplier. Usually multipliers are big designs. Let's see multiplier 16, and we will open both the scripts. So this is the DCTCL one. We will search for violated here, and we see that okay, area is something 2766, and the stack is there's no negative stack here, as it's shown by the report timeline. Let's open the earlier one. Let's search for violated, and now we see violations. So we see big violations. Why? Because the input delay, input external delay, and what is the problem here? Okay, this is input to flop. The input external delay is the library hold time is so big here because of some issue in the constraint. The library hold time is pretty big, so there's big violation here. So we see that earlier there were big violations, but now because of the characterized write script, we get some accurate timing constraints, and the violations are virtually reduced to 0. There are very few violations in some of the design. So this is where you work. Even if you, so this is where characterized write script help you. You don't have to spend so much time in writing out constraints for each and every sub design if you want to characterize. You can start with some jump constraints, and then characterized write script will do a good job for you. Right? It will take care of the interface timing. Obviously, the top level, the port level input output timing, you have to be careful about. So in this case, for example, the ports that go from the ports that exist at chip level, you have to write good input and output delays for that, because characterize will not work on that. Characterize will work at, we saw that adder 16 is directly connected, the adder 16 input pins are directly connected to the top level ports, and the input delay in this case is not changing. So the top level input and output delays will not change. Only the input and output delays with respect to the hierarchical designs will change, because now DC has information about interfaces. So let's look at the cascade thing, cascade underscore DCTCL, and see violated, area is fine, and then there is no violation, which is good. And I guess cascade does not even have now, it does not have the GTech logic, because now the comparator was compiled. It was compiled once. In the first pass, the comparator was being compiled after cascade mod, but in the second pass, let's look at the recompile script again to understand it better. Yeah, so we started from this cascade mod DDCL, we compiled, and yeah, so we set the report file, and we wrote out the report. Let's look at now. In this case, what is happening is that let me see let's see what all it wrote out. DDCs are written out. Yes, DDCs are written out, and then what about netlist? Is there any netlist written out? No. Now let's do the last step. So we did the first compile, initial compile, the second pass compile, the characterize, and then second pass compile, and now we'll write out the DDC, and we'll also write out the netlist. We'll write out also the netlist, let's use the same command. Netlist dot, let's say netlist dot read and format. So we wrote out netlist here. So we wrote out the netlist. Let's open this netlist. Let's find out if there are any GTEC components here. There's no GTEC here. So that problem got solved because we compiled the design the second time. So first time it was already compiled. Now let's look at. So there are no chip level timing reports here. Although I would like you, whenever you work, I would also like you to add chip level timing reports because that is the most important criteria. Now let's do some chip level timing analysis. We will do. Let's remove all the designs. Let's read DDC of the chip level. We will read the initial DDC. I want to point out a very important thing. I'll link and I'll do a report timing because it's a DDC, it contains all the. Or what I'll do report constraints minus all violators. So we see that there are some setup violations here. So we will note down this and we will copy it. And then I will remove the design again and I will. So let's also see what kind of violations happen. So this is a violation from input port to the register, and register is inside multiplier. So this is a particular violation, right? Are all these violations of a similar nature? Look at there are 4 violations. Data 16, yeah, all the violations are similar type. Now I'll remove the design again. I will read DDC and now I'll read the final DDC. I'll do a link and I'll now report constraints minus all violated. Now the design has no violated constraint. How did it happen? Although there were violations from input port to register inside multiplier, how did it happen? Now, if you compile the design using single pass, using top down, there will not be any violation. Okay? But we did not do that. So how it happened is that in the first pass, now please remember we did not compile the chip from the top. We did a bottom up. In the first pass, if you remember, we did synthesis for multiply 16 by 16 separately. We changed the current design to it. We had some default set of constraints. And we synthesized multiply 16 by 16. And then we characterized it and wrote out the second set of constraints. Now whenever it was compiled the first time around, initial synthesis, the compilation did not optimize this path very well because the input delay at the multiplier level was some non-optimal value. When the characterize command wrote out the input delays, the new input delays, these new input delays were very realistic, and in the second pass compiled, DC was able to do a better job. Therefore, in the final netlist, we don't see any violation, but we see a violation in the initial pass. This is the summary of characterized write script. This is how it helps you. It is the most accurate way of writing constraints for a hierarchical design. So if you are confused about which synthesis methodology to take, the design compiler capacity and the number of cores in the machines and the memory in machines have been growing. So every year it's getting more possible to compile a design top down, which was not possible a few years back, or which was not practical a few years back. So I would recommend still, if you are working at any design, or if it's not a big chip, then think about the top down. and make sure you have a top level constraints are available. If it is not possible, if top down is not possible, go bottom up, arrange your stuff in the similar fashion which is shown by this example. Use characterize write script only when it doesn't take days to complete or number say more than few hours to complete. If characterize write script is taking more than few hours to complete, then rethink about that and maybe go with the direction that people do fifth level, that is they compile, they synthesize the block separately, and at the top level they just read the black box and don't but in this case you have to make sure that your hierarchical designs input and output delays are very good, because obviously manually you will not be able to do a job as good as design compiler. So now you know all the three ways to do synthesis: top down, bottom up using characterized write script, and bottom up using black box. So I hope this was a useful session. Thank you.